Mul-Ty the Tasmanian Tiger is a 2002 3D platformer collectathon made by Australian developers Krome Studios. In 2016, the game was remastered for modern consoles, including a PC release. And in 2022, I joined the speedrunning community and made it my mission to bring online multiplayer to the game. This video documents the history of Mul-Ty-Player's development and hopefully provides some ideas for other communities wanting to introduce multiplayer to their games too. Before we start, a special thanks needs to go out to Krome for their work and commitment to the games industry. When 3D game development was still in its infancy, they managed to build not only an incredible game franchise, but also the engine it runs on, with only a small team of incredibly talented developers. I really don't have the words to express the community's love for Krome, so instead, here's a montage we created to thank, and maybe scare, Krome's quality assurance team, in case they see this. Okay, so I'm Matt. My programming experience before Mul-Ty-Player was lacking. I'd written a Discord bot once and messed around with Unity, so I knew some C#, but was definitely not a competent developer. This was all new to me, so let's start with how I even got involved with Ty. I picked up Ty back in 2022 as my first speed game. I'd been interested in speedrunning before, but I hadn't really tried it. Ty seemed like a great starting game since I played it a lot as a kid. A few months into running the game, I became interested in the technical side of the game. Modding's been made relatively easy over the years by the modding team, but special thanks here must go to Florals for her insane knowledge of the game files. For the uninitiated, most games from the 2000s had their files bundled into one or more large archive files to make transferring them to disk faster and easier, as well as adding a layer of copyright protection. For Ty, this comes in the form of the .rkv file. The key RKV files include the data RKV, which stores the game files, the music RKV, which stores the audio, video for the video, and then since version 1.44, there's an override RKV, which stores the shader files. Before I'd even joined the community in May of 2022, the modding team discovered that Ty checks for files in PC external and PC specific directories on launch. These need to be made manually, but once they're created, the game will sideload certain limited files copied to these directories, using them over the ones contained in the default RKVs. A debug build, accidentally released by Krome and made accessible through the Steam database, gave us access to a modified OpenAL32 dynamic link library, which for some reason forces Ty to sideload any file in these directories, but with a cost. It breaks the level select in-game, and it restricts the player from entering boss fights normally. A few months into the development of this project, Florals had a breakthrough for modding. She found that the game also looks for a file called patch_pc.rkv on launch. Repackaging files into an RKV with this name enabled sideloading without the need for the modified DLL. A backbone to all Ty modding is the LV2 files. Each file is a text file passed by the game to determine the placement of objects as well as some of their local per instance properties in that file's corresponding level. LV2 editing was vital to the success of Mul-Ty-Player, but more on that later. For those unfamiliar with game hacking, Cheat Engine is a powerful tool that allows you to view and modify the active memory of any application. My initiation into Ty-related projects was an Opal distance tracker, which acted similarly to Mario Odyssey's Balloon World minigame, allowing players to set an Opal position and then for others to try to find it by using the Opal count as a distance tracker. This taught me how to find memory addresses in Ty using Cheat Engine, and then how to perform memory manipulation to modify the data at these addresses at runtime. The idea is to use low-level function calls to write bytes to specific memory locations in an external running process. I won't delve into intricate details since this method is associated with malware creation, but used responsibly it becomes one of the biggest driving forces behind swathes of game modifications. This provides the capability to alter nearly anything at runtime. Yes, Krome, if you're watching this, that is Steve in Taiwan. If you want to know how I did that, then you'll have to pry the answer out of my cold dead hands. Having experimented with memory writing, Lorne, a fellow speedrunner, approached me about making a speedrun ghost/replay mod. I was initially skeptical due to the sheer complexity, but Lorne posed a simpler question. Hey Matt, is it possible to move a tree or something? Intrigued, I entertained the concept. First I needed a way of getting the position of an object. The LV2s were perfect for this. Recall that these contain the positions of objects, so I chose a random tiki torch in Bridge on the River Ty and found its position. Then I leveraged Cheat Engine, searching for its floating point y coordinate, or height, and found a few results. Changing the value of these results to be 100 units larger and tabbing back into the game, the torch had moved up. And Lorne and I both knew at this moment that we were onto something big. So the next day we jumped into a call to discuss how we might go about syncing the positions of players over a network. As programming and networking was still new to me, I had to take a few days to research and stumbled upon Riptide Networking by Tom Weiland. It's a lightweight C# networking solution using both TCP and UDP packets. I won't bore you with networking code, it was relatively easy to figure out, and soon enough I was sending data back and forth through a server. So the overall concept behind Mul-Ty-Player was to have all players play on their own single player instance of the game, and then to grab certain parts of the active memory, send them to a server, manipulate them, send them back down to all other players, and then write them back to the running memory. For example, we can get the player's position, send it to the server, send it down to all the other players, and then write it to the position of an avatar object. By doing this repeatedly, it updates as the player moves, so all other players see this object as if it is the player. For the avatars, or player representations, we already settled on the koala kids. They're small, they're distinct, they're lovable, they're great. However, creating new objects in memory at runtime proved challenging. The answer was to avoid trying to generate the new objects via code altogether, and instead to modify every LV2 file to add the koala kids far out of bounds in each level. This alone wasn't sufficient. I also needed to include a koala kid objective in each level, as well as a way to activate it. So I hijacked the scripting system used in the LV2s to activate the objective at the start of every intro cutscene, and for levels that didn't have an intro cutscene, I added a trigger sphere to the start of the level, which activates the objective when entered. Rainbow Cliffs was a bit weird here. I had to add several trigger spheres, since the spawn point changes depending on which level you've entered from. Understanding statically and dynamically allocated memory became crucial throughout this project. Static memory is always allocated in the same place relative to the starting point of the application, or the base address. Dynamic memory isn't. Importantly, static memory is always loaded throughout a program's execution, which is why its memory locations don't change. Most of the things we've been messing around with in memory this far were statically allocated, like Ty's position in the world. The koala memory was dynamic. Never having encountered this before, I was immediately confused as to why the addresses I'd found for the koalas stopped working whenever I reloaded the level. It turns out I needed something called a pointer path. Think of it like the treasure chest in Rex Marks the Spot. You know you want to go to the final chest, but you don't know where it is. So you go to the first one, and that tells you where the next one is. And then the next one tells you where the next one is, until eventually you end up at the last chest. Now imagine that they aren't chests, but instead locations in memory. Each memory address containing the address of another in a chain until you end up at the destination. For any given value, there might be hundreds or even thousands of pointer paths of various lengths. The hope here is that at least one of them uses addresses which are consistently pointing to the same structures. That way, by following the path, we always end up at the desired data, even if the location of the data changes. In Cheat Engine, we can do this by scanning for pointer paths on the desired location, then reloading the game or level and ensuring that the path still points to the same data. Once we have our pointer path, it still needs to be programmed, so this function must be used. It allows us to follow the pointer path to the destination and then returns the discovered location. This is great, but it adds complexity since this path may need to be recalculated when the level reloads. Koshi, the modding guru behind the RKV tools, elucidated the concept of pointer paths, and this insight, along with an hour of debugging, allowed Lorne and I to achieve the first online movement, albeit out of bounds on a random platform in the sky. There are a few problems to overcome, however. Firstly, the koala kid objective figures out how many koalas there are in the level by counting them and setting the count dynamically. In Snow Warriors and Beyond the Black Stump, after adding the 8 player avatar koalas, this led to the required koala count to finish the main objective being set to 16. That causes the objective to be unbeatable. We needed to manually reset the expected count to 8 when we're in these levels. Another issue arose with the koalas in Snow Warriors and Beyond the Black Stump, where some of the objective koalas were being moved instead of the ones I'd placed. After some messing around in Cheat Engine, I noticed that the koalas are always loaded into memory in the same order. Katie, Mim, Elizabeth, Snugs, Gummy, Dubbo, Kiki, and Booney. If duplicate koalas are defined in the level, then the koalas are loaded in pairs, so in order it would be Katie, Katie, Mim, Mim, Elizabeth, Elizabeth, and so on. The easiest way to handle getting the correct koala was to use a modifier to offset the position in memory by 1 koala's worth, specifically when in Snow Warriors or Beyond the Black Stump. Next, there was the issue of ensuring that the koalas can't be collected by Ty. In the LV2s, each koala has a safe to leave flag, which determines whether they can be collected by Ty or not. Since this is in the LV2s, we don't need to do any wacky memory manipulation. I also needed to remove the collision from the koalas. I mean, it would be no fun bumping into each other constantly during play, and luckily for us, there's a single byte which can be toggled to turn collision on or off for most objects, including the koalas. Unfortunately, this really still wasn't the end of the koala movement stress. In the level Outback Safari, the player controls the bush pig instead of Ty, and the bush pig, of course, has a different position and rotation memory location to Ty. So we check if the level is Outback Safari and then modify accordingly. Finally, we tried testing it all, but no koalas appeared. The koalas spawned far out of bounds, were out of range, and unaffected by Mul-Ty-Player changing their position until we approached their hidden location. I needed to find a way to artificially increase the draw distance. Ty uses a file called global.model to define the global properties of every object and character in the game. Each object has an update distance and a draw distance. I found each koala and appended a few zeros to their draw distances. The draw and update distance values in global.model are multiplied by the integer representation of the game's draw distance setting. On low settings, it's multiplied by 1, on mid by 2, and on high by 3. Consequently, I needed to update the draw distances for all collectibles and various in-game elements later in the project. After all of this, here's the first video we ever took of koalas moving around in Mul-Ty-Player. Around this time, the first attempts at speedrunning with Mul-Ty-Player were carried out to very limited success. Unfortunately, the app was a buggy mess and was very hard to use. I mean, it was still a command line interface with very little to help the players. The first major tests were an any percent and then a 100% speedrun race between myself and a runner known as SilentKuudere, who has helped beyond words with the testing of the application over the last 2 years. These tests were cut short in Beyond the Black Stump, where Booney turned pink, and more importantly, speaking to Ranger Ken immediately crashed the game. The cause of these problems was a race condition. Race conditions commonly arise when two processors attempt to access the same memory location. In this case, the koala positions. Setting the koala memory addresses in the Mul-Ty-Player client during level loading posed challenges. If done before the game loaded the koalas, it could lead to the memory positions calculated from their pointer path being invalid or incorrect, resulting in crashes or erratic behaviour. The key problem here is knowing which byte to use to determine when the game has loaded, and making sure that that byte changes after the things we need to interact with have loaded. In reality, this byte has changed several times over development. Recently, however, I identified a valid byte to determine when the game has finished loading in the game camera memory. I had absolutely no front-end development experience whatsoever. So I decided to try learning Windows Presentation Foundation, or WPF, in a day. Don't do this. After a week of struggling, a lovely member of the modding team, Kana, offered up her help. She was already experienced with WPF and gave me the kickstart I needed to make a solid UI. Functions previously managed by commands were seamlessly integrated into buttons and visual elements, and the UI now displayed each player's level code, name, selected koala, host status, and other relevant information. Amidst this, I tried using AI to upscale the koala textures and rigged up their models to make animations when you select a koala. I also packaged these upscale textures in with the patch file, so everyone gets to see high definition MIM. Why would you not? We also integrated FacePunch, a .NET wrapper for Steamworks, to fetch the player's Steam name to use as their display names when connecting. Undoubtedly, the UI was the largest time sink over Mul-Ty-Player's development, largely due to WPF being complicated to work with. But that really isn't that interesting, so I'll leave this section short. Needless to say, Kana's assistance played a pivotal role in pushing the project onwards. So while Kana focused on refining the UI, my attention shifted to writing the collectible syncing system. To start, let's define some terminology. The live data of each collectible refers to the loaded object in a level, encompassing its visual representation, collection method, state, and various other properties. Specifically here, I'm referring to the memory block for the visual object. The save data of each collectible refers to its state as collected or not in the save file. To sync collectibles properly, it's important that I sync both the live and the save data. By syncing the live data, players in the same level will have the collectibles disappear once someone else has collected them. And by syncing the save data, players in other levels will have their games update what has been collected too. First, we define a sync object. Each sync object represents a thing we want to sync, such as the Thunder Eggs or the Opals. For each object, we then define an observer. This is used to signal to the client when a change occurs, and is important to reduce the number of memory reads for each gameplay cycle. For example, if we try to read the opal count, that only requires 1 memory read per frame. If we try to read the state of every single opal, that requires 300 memory reads per frame. When an observer changes, the read data function is called. This reads the state of every collectible, usually only in the current level, searching for a change. Current level data and old level data arrays are created to store the data for the level-based collectibles and allow for comparison between previously read data and the current data. When a level is loaded or someone joins the server sends all of the data down through the clients, ensuring that they are up to date. When an object is found to have changed state according to a condition check, it's updated in the collectible's global object data, which is persistent for all levels, and its index is sent to the server. Here's where things get complicated. The index of a collectible in the save data does not necessarily match its index in the live data. In other words, the collectibles are not necessarily loaded into memory in the same order as they appear in the save file. Luckily, most of the collectibles have an ID somewhere in their live block of memory, so we can use that to find the corresponding save data index. So we have 2 indices, the save index and the live index. They're both sent to the server, where it gets updated in the global data for the server, and then it's forwarded down to the other clients. Once the data is updated, a save syncer class is used to sync the save data, and a live syncer class for the live data through the save and collect functions respectively. All of this is handled through abstractions of functions with a default implementation, using the virtual keyword. This system enables the creation of syncing classes like this. It's really short. We only need to define the collectible properties. The intricacies of synchronization are managed behind the scenes, but allow us to easily override the functions for more complex, collectible-specific syncing logic. Thunder Eggs and Golden Cogs are easy to sync, since the game autosaves when you collect one. Opals don't have this feature, and their collection status is not updated in the save data until the game saves. This intentionally prevents many complex calculations during gameplay, building a backlog of opals to perform calculations on before they are all executed at once during a save. Opals are also stored in the save data in a really tricky pattern. Firstly, opal states in the save data are 1 per bit, not 1 per byte. Directly navigating to the opal's position in the save data becomes impractical. Instead, we have to calculate its byte index with this division, read the current value of the byte, calculate which bit should be changed using the modulo operator, and lastly use bitwise operators to left shift 1 by the bit index and OR it with the value we read earlier before writing it back to memory, essentially flipping the bit. Opals are either spawned from crates or just sat out in the open. The live data for these 2 types of opals is segregated in memory, and crate opals in the save data are stored in reverse order. If a level has 270 opals outside of crates, and 30 in crates, the opal with index number 299 corresponds to the opal at bit number 270, indexed from 0, in the save file. The opal with index number 270 is the last opal in the save file for that level. I can't do the explanation justice here, so I wrote a very loose mathematical proof explaining why this specific line of code needs to exist. Pause and read this at your own peril. Good luck. I found early into experimenting with opals that they have a magic number state, which is just a byte that when changed causes behavior change rather than a value to change. The opal state spans from 0 to 5. 0 despawns the opal and is the initial state for crate opals. 1 spawns the opal and is the default state at the start of a level for opals in the open, or on crate break for opals in crates. 2 is just for the opal resting on the ground. 3, the opal is pulled towards Ty for collection. 4 saves the position of the collected opal, and 5 marks collected opals, preventing them from respawning. Setting the state to 3 causes it to be pulled, accelerating towards the player regardless of distance, and end up as a collected opal with state 5. A choice surfaced, whether to set the opal state to 3 for all players, allowing them to witness the pull and hear the sound, or to set it to 5 for silent collection in the background. The determining factor was the super byte count. A super byte is awarded in Ty after collecting 100 opals without reloading the level. Opting for a silent update prevented opals from contributing to the super byte count, so I opted for setting the state to 3. Another fun interjection for Krome here. Though impossible in normal play, collecting an opal, saving it, reloading the level, and then setting the opal back to being visible causes it to display with transparency, similar to previously collected Thunder Eggs. Syncing the portals was incredibly fun. Each portal has a magic number state allowing us to show or hide portals as we wish. For syncing, I defined an array of portals which are initially hidden. The portals are then activated by one of 2 cases. A player has entered the portal, or that portal is spawned by any other means. Unfortunately, there is no single memory address that can be used as an observer for the portals, so instead, the portal handler monitors the states of all portals when in Rainbow Cliffs, and the number of times each level has been entered when not in Rainbow Cliffs. Finding a solid observer for the crates was also tough. Eventually, I identified a memory that changes when the crate breaks, likely tied to the sound played on break. Once the crate has been found, its index is sent to the other clients. Crates are not saved, ever, so we need only handle the live data. Crates conveniently hold pointers to the objects they contain near the end of their live data, so by following these pointers for the number of opals in the crate, we can set the opal state from 0 to 1, which causes them to spawn, and then we manually despawn the crate. Synchronizing the bilbies was also pretty tough. The central issue emerged when a player collected the final bilby but exited the level via the main menu or exit level or Alt F4 or a game crash or whatever before collecting the Thunder Egg. In this scenario, the Thunder Egg remained uncollected, but the bilbies were synced and the final bilby was absent for other players. Upon the player's return to the level, the bilby was already collected, so it would be despawned by Multi-Player and create a softlock. Krome already fixed this issue at some point through development by setting the state of the final bilby to be collected in the save data to 3 instead of 1. When the save data is passed on entering a level, if the bilby Thunder Egg is not collected but all bilbies are, it looks for the one saved with the 3 and then spawns it so the Thunder Egg isn't lost. Regardless of the safeguard Krome put in place, the client would still see that bilby as synced and despawn it. The solution was to leverage the Thunder Egg syncing. Rather than syncing all of the bilbies, the multiplayer client refuses to sync the last bilby collected in a level by blocking bilby syncing when the level's bilby count is 4. Only once the Thunder Egg is collected does the bilby sync for other players. This way, if someone leaves before getting the Thunder Egg, it's as though they never even got the bilby. Okay, so one thing I've glossed over here is how exactly the client and server communicate the collected object indices. Well, Riptide, the networking API, uses a packet system where you build a message, add data to it, give it an ID, and then send it. Then, using C# attributes, we define a message handler which handles incoming messages with the same ID. To streamline this process, a single message is created for all sync objects, avoiding clutter in the message IDs. The sync handler class manages sending and receiving sync messages. The collectible sync message class then acts as a wrapper for the default message data, including the live and save indices, a level ID, and a unique string identifying the collectible, like cog or bilby. It features methods to create and encode the message, and then on the other end, decode the message. All sync messages are handled in the sync handler class, which contains a dictionary of the sync objects with the unique string identifiers as keys, and the base class of all of the objects, the sync object handler, as values. Since all of the object handler classes inherit from the sync object handler class, calling any function is simplified by referencing the base class through the dictionary given the identifier. We're essentially using generics here. Then, the unique per collectible functionality can override the function. The only place where a massive if statement is needed is when the observers are checked. Even these aren't necessary, but by using these if statements, each sync type can be toggled on or off using the server settings and propagated down to the clients. During the time attacks, the game actively conceals the collectibles and enemies and disables triggers, presenting challenges for synchronization. All koalas are hidden during the time attack, so I had to find out which byte was being changed and force it back so we can see each other, and even competitively race the time attack. Another concern brought up early into development was around the in-game leaderboards. Speedrunning the game with multiplayer inevitably means that the run times on the in-game Steam leaderboards would be skewed heavily. Whilst we know there will always be a few people cheating times, intentionally or otherwise, we didn't want to add to this en masse, so the simple solution was to set the timer to a very large value as soon as you connect to multiplayer. Tinsel is a Taiwan speedrunner with vast programming experience.
Crikey, what the f*** are you doing over there, you dumb
who is either the villain or the hero of this story depending on where you stop. A few months before the dedicated servers went online, Tinsel got interested in the codebase for multiplayer and I ended up on a call with him and Lorne where Tinsel was profiling the app and looking for issues. He found a lot. He found a lot. There were redundant memory writes, duplicate loops, unhandled errors, bad code flows and various other rookie mistakes left from when I'd started, so Tinsel tried to fix it. He systematically tore the application apart to what was necessary and rebuilt the missing or broken pieces. This fixed a lot of the crashing, but with a pretty big cost. Tinsel unintentionally broke almost everything after the final public release in April of 2023. Then life took over and he didn't have time to work on the app anymore, so I was left with a broken codebase that I couldn't navigate properly, and that wouldn't even build. The app remained this way for months. During the hiatus, I worked on other projects, like porting the Mercury 2 models to Mercury 1 model formats, or starting a troll mod for Ty, reverse engineering formats from other games, and tried messing with Ty 2 and got some pretty solid results. I plan on coming back and finishing Mul-Ty-Player in the future, but for now, here's what we ended up with. While we're on the topic, I would love to thank whoever the artists were at Krome who purposely made the koala kids in Ty 2 match the kids from Ty 1. I don't know that anyone had noticed it previously, but it was such a lovely detail to pick up on. At the same time, the speedrunning community's love for Mul-Ty-Player was dwindling. The remaining runners fell in love with a new category called 100% level locked. Sure, 100% was fun, but it was essentially each player doing part of a normal 100% run with barely any interaction, so Lorne suggested a category where everyone has to stay in the same level until that level is 100% completed. This remains the most popular speedrun category for Mul-Ty-Player by a country mile. Flash forward to September 2023, where Tinsel expressed interest in revisiting Mul-Ty-Player. We hopped on a call and made a list of all of the issues, running meticulously through each of them one by one. It was the first time in over 4 months that a build of Mul-Ty-Player had run, and it was clean. Along the way, I learnt what he'd changed and why, and used it as an excuse to rewrite some stuff myself with my new knowledge of WPF. Yes, I called you a villain earlier, but thank you, Tinsel. No single person has done more to help with this project than you, and I will always be grateful for that. Mul-Ty-Player would still be a buggy mess that crashes on launch without your support, and your suggestions, and your advice. Seriously, dude, thank you. With new updates being possible, I set myself to work on adding several new features, including a large GUI update, objective syncing, which I'll discuss shortly, and a new game mode to aid with the new category. The primary motivation for the new mode was to address a lack of clarity on when to progress to the next level in runs.
Alright, hey Brian.
Scott, go, leave.
Did someone get ringed?
Yeah, everything's done, everything's done. I was on Game Info, we're good. Recall that the rules of level lock require players to be in the currently active level, or Rainbow Cliffs, until it's 100% completed. This meant runners were relying on communication, which was inconsistent. So level lock mode overrides the portal syncing code, forcing all portals except the current levels to disappear, so another level can't be entered. When the level is detected as complete by the server, a message is sent down to the client, forcing open all portals that should be accessible. A list is used to manage portals that should not be open. When one of those is activated, for example by entering a boss level, that level will be removed from the list and remain shown when all portals are enabled. Additionally, the triggers which allow the player to go into the boss levels are handled alongside the portals, avoiding players entering boss levels early. Finally, I added a sound alert for when the level is finished, so all players know exactly when the portals have opened. To coincide with the huge UI update, I wanted to add objective syncing. Ty has certain Thunder Eggs which are obtained by completing an objective. These vary from turret shooters to escort missions, and just about everything in between. The ones I was interested in are the collectible missions, which ask the player to collect X number of things and return them. Up to this point, one person would be responsible for starting the mission, collecting all of the objects, and handing in the mission. With some objects scattered far, it was imperative that I made it possible for anyone to help with these objectives. So to start, I defined an abstract objective class, and gave it an object count, data array, and objective state. The objective state is an enum with 4 options. The objective is either inactive, which is from before the objective has been activated by a player, active, which is when the players can now collect the objects for the objective, ready, which is when the final collectible has been collected and the objective is ready to hand in, and complete, which is when the objective has been handed in. Next, I defined a function, runCheck, which switches over the objective state and activates different functions depending on the state. When the state changes, an event is raised, which I've subscribed run action to, allowing me to run code once when the state changes. I also defined functions for activating objects, setting the objective state, sending activated object indices to the server, and sending memory addresses. I then made an objective handler similar to the sync handler, which objective-related sync messages are funneled through. It contains a dictionary with the synced objectives as values, which acts as a registration of the objectives. Defining objectives by type, I can reuse the repeated KoRLKiller objective for both Snow Worries and Beyond the Black Stump by registering both as KoRLKiller objectives but with a different qualifying level ID. This level ID is then checked against the current level of the player at runtime to determine if the objective should be actively running its state. It's around here that I was noticing a pattern allowing me to find the active memory of any object in the level. First, note that the name of every object is loaded into memory somewhere when a level loads. This is immediately followed by what I can only assume is the name of the prop used to search for the object in the files. Immediately after this, we have a few bytes of padding, followed by an address. This address always points to the first object of the above type in memory. This is incredibly useful, and it's the method I use when researching data structures for the objectives, and for anything now. I started with the burner objective in Bridge on the River Ty. A data structure emerged very similar to what I'd already seen with the KoRLKiller objective. This structure holds for all objectives. There's a currently collected count, a total for the objective, and an objective active state. Typically, each of the object's live blocks immediately follow the objective memory. The first step in syncing an objective is to figure out how to activate it for all players, so I checked what exactly was happening when the burner objective was activated. I took screenshots of the memory before and after activating the objective and compared. Once I'd found the bytes that changed, I checked what each of them did by manually setting them, and finally programmed the client to change these bytes when the state changes to active. Then, I coded the isInActive function to monitor the burner objective activity state when in Bridge on the River Ty, and when it changes, send it to the other players. I then repeated the process for the burner object itself and wrote the isActive function to iterate over the burners when the burner count increases, looking for the changed burner. Once found, the index is sent to the other clients where it's written to memory. Next, there's the transition from active to ready for turn-in. This might seem simple at first, but I couldn't find a magic number which sets it ready to be turned in. It doesn't trigger off of having all of the burners or the objective activity state being a specific value. It specifically seems to trigger on a burner being activated such that the current count matches the total count. Since handing in the objective relies on a trigger, I turned to the trigger itself. So I added a new trigger handler class and encapsulated the logic for activating and deactivating triggers based on their index in the loaded object memory, which happens to match the LV2 order. I then found the trigger which gets activated when burners are all collected. Once the client detects that all 8 burners are activated, it sets the objective state to ready and sends that to the other clients, where they force that trigger to activate, allowing anyone to turn in the objective. Syncing the koala kid was similar, with the only major difference being that each koala has a magic number state which triggers their collection when set to 5. This avoids the need to manually detect when the objective is complete, but due to issues with synchronization, we do it anyway and force the trigger to be active on ready for turn. Next, I looked into the seahorse objective. Krome somehow managed to make the seahorse objective statically allocated while all of the other objectives are dynamic, so the seahorse objective is always loaded and there's only ever one instance of it. While the remaining logic is akin to the other objectives, there's a noticeable difference in how the objective is completed. Typically, a radius around Aurora checks for the presence of the seahorse babies, but in multiplayer, since only the seahorses that a player collects follow them, with the seahorses collected by other players disappearing entirely, this could make handing in the objective impossible. The workaround I used was to manually add my own trigger to the LV2, which triggers the cutscene for the Thunder Egg. Then I can force it to be active, the same as with the burners and koalas. Next was the cable car syncing. The general logic for starting and ending is as previously described, but in this case, the goal is to defeat all 6 frills on the watchtowers. These frills, however, are not a unique type of object, and they are mixed in with the normal frills in the LV2. Fortunately, they are loaded in the same order as defined in the LV2s, so I noted down which indices are the cable car frills and put them into an array used to only sync the correct frills. Similar to the koalas, the frills have a magic number byte for their state. When this is set to 8, the frill dies, so I need to write 8 to this byte when someone kills one of the frills. The final objective type synced to date is the treasure chest objective in Rex Marks the Spot. Instead of having an objective, it's merely a chain of triggers, each activating the next. To sync the chests, I used a data array to store a byte for each chest. Since they must be activated in order and there's no way around this, the number of bytes in the data array, which are 1, is used to determine the current chest, which just means the chest which needs to be activated or interacted with next. Once activated, the data will update, causing the count to update, and then the trigger for the next chest, along with the chest itself, will be activated and shown. The objective is deemed ready for turn-in when the final chest and its trigger are activated. While working on this, I noticed an error with the scripting in the vanilla game. The LV2s use a trigger and event system to handle interaction between objects in the level. For example, the Thunder Eggs have an onCollected event, which is triggered when the player collects the Thunder Egg. When raised, it looks for an object referenced as the target and runs a named command like activate or hide on the targeted object. The trigger box and trigger sphere objects are designed to allow interactions when the player moves into, out of, or presses the action button inside a defined space. These triggers use the onEnter, onExit, and onAction events. A new issue arises when multiple objects should be triggered by one event. For example, if we want to play a cutscene and show a Thunder Egg. There are two ways of doing this. Firstly, you might be able to chain events. Each cutscene is played by activating a dialogue object, but the dialogue object also has an onCompletion event. So you could, in this case, trigger the dialogue when onEnter is raised from a trigger sphere, and then show the Thunder Egg when onCompletion is raised by the dialogue. If chaining isn't possible, like when you're trying to activate two portals to appear, for example, then the script object should be used. The script object allows delaying and triggering of multiple objects or messages off of a single event. So to get back to the error I spotted, if our goal, as Krome, is when the player presses action in a trigger sphere surrounding a treasure chest to play a dialogue, activate the next chest's trigger, and make the next chest appear, we might try doing something like this, where we make the first trigger sphere activate the first dialogue when onAction is raised, and then when onCompletion is raised, trigger a script which sends activate to the next trigger and show to the next chest. This is not what happens in the unmodded game. A script was not used, so whoever hooked up the logic failed to show the chest and activate the trigger off of the cutscene completion. The next chest is clearly shown on completion of the dialogue, but where is the next trigger activated? Here. On exit of the original trigger. So in theory, we can run up to and then away from a chest, and then go to the location of the next one, and despite the chest being invisible, yeah, the trigger is active. All of the chests are incorrectly scripted in this way. The fix for this is simple and limited to the LV2, so I'm able to do that without any access to the source code. Yeah, let me know if you want the file, Krome. I've done it. In gratitude to the community, a final game mode, Hide and Seek, was added to the project. The core concept is this. Each player is given a role which can be changed at any time. When all players declare ready, a countdown of 75 seconds starts. The Seekers are then locked in place, and the Hiders are teleported to the start of the level where they run to hide. When the countdown ends, all Hiders timers start counting up in the client, and all Seekers are unlocked from their position. When a Hider and Seeker are within range of each other, a message is sent to both, awarding the Seeker time for their catch and teleporting the Hider to the start, changing their role to Seeker. This continues until all Hiders are found, where everything except the timers is reset.
Hi, it's me. So this was supposed to be the end of the video, but in March of this year, 2024, just when I thought that the project was finished, a certain someone was messing around with the memory of Ty again. That's right, it's Tinsel. No, it wasn't Tinsel. Who was it? It's the Germans, specifically Buzchy. This guy single-handedly convinced me to keep working on Mul-Ty by finding features that we never thought would be possible. Here's some honourable mentions before I go into more depth. When Buzchy first approached me about Mul-Ty-Player, it was largely because of a few features that Lorne had been requesting for well over a year. The first of these was the ability to force players into a level. Buzchy had found that by changing a specific byte to a level ID and then setting this magic number, we would be immediately teleported into the level that we set. And while Buzchy solved several other requests, I went back to something Lorne had been asking for since Mul-Ty-Player's inception. Lorne wanted to use the entry glow object from Final Battle to display the other koala's positions. Once I'd placed a glow in the level, I tried moving it, but something weird happened. The glow would only be visible when looking at the original position. Buzchy and I spent a while trying to find any related position address, but came up empty. So I had this silly little idea of making the glows big. Like, so big that they can't really be seen from anywhere, but they are technically everywhere. Then we just scale them down when we need to use them. Yeah, that worked. Finally, one morning I started experimenting with some memory Buzchy and I had looked at the night before. I quickly found what looked like FreeCam. We then spent over 12 hours on a call, figuring out how to use this to create a new mode for players joining a server, allowing them to go into FreeCam and spectate the other players. I even added a slightly janky camera lock on to follow players moving around. Since this mode, not much has been added, but there are still plans for new game modes and events to keep this project alive. And that's a wrap on Mul-Ty-Player. To try to keep this short-ish, plenty of information has been omitted, so if there's anything further you want to know about the project, or if you want to contribute to the project, feel free to leave a comment or join the Time Modding Discord. Please try Mul-Ty-Player for yourself. It's relatively easy to set up, but a full guide is linked below along with a link to the download of the app. Thank you again to Krome for being such a kind and friendly group of people and making this incredible game. The sense of community fostered from it is staggering. That's all I've got. Thank you for watching this video.